To store a list of data, a computer's most basic instinct is to use an array. An array requires contiguous memory, a single, unbroken block of physical space to house every element side by side. This rigid proximity is what makes arrays fast. Because the hardware knows exactly where the first item is, it predictably jumps to the second, third, and fourth without searching. It simply reads the physical sequence. But as a system runs, memory gets messy. Programs open, close, and claim blocks of RAM at random, leaving behind a fragmented landscape of isolated gaps. When an array needs to grow and the space immediately next to it is already occupied, the system hits a wall. It must pause execution, search the RAM for a larger block of contiguous space, and physically copy every piece of existing data over to the new location. Relying on physical memory adjacency creates a performance bottleneck. When applications handle thousands of dynamic insertions, physically relocating data repeatedly is inefficient. The solution is to break the sequence apart. We can store each item in scattered, non-adjacent memory addresses, wherever there happens to be free space. To keep the logical order intact, we use pointers. Pointers are explicit directional references, metadata that tells the computer the exact address of the next isolated piece of data in the chain. In languages like C, you manage these memory addresses directly. In Python, the logic is handled by the interpreter. When you assign an object to a variable, you are storing the memory address of that object. Python variables function as implicit pointers. Pointer architectures trade the predictable speed of physical adjacency for the freedom of dynamic memory distribution. The foundational building block of a pointer structure is the node, an independent container divided into two parts. The first part is the data attribute, which holds the actual payload. The second part is the next attribute, a pointer that is initially set to none. Assigning the next attribute to another node's address links them together. The connection only travels forward. Eggs points to ham, but ham has no reference back, forming a singly linked list. To terminate, the final node explicitly points to none. With just a payload and a forward pointer, this chain creates a logical sequence without requiring a contiguous block of physical memory. This singly linked list has a vulnerability. To append new data to the end of the sequence, you first have to find that end. Mapping execution time against data volume, finding the end requires checking every node until none, a linear O of n time complexity. As the list scales into the millions, the computer performs millions of redundant checks just to add one element. We resolve this by adding a tail pointer to the singly linked list class. This tail variable provides a direct memory reference to the final node. Appending a new element now bypasses the traversal entirely, keeping the operation at O of 1 constant time, regardless of list length. We apply a similar optimization to the length. Updating a size attribute during insertions and deletions removes the need for an O of n counting loop. By tracking the head, tail, and size as metadata, operations that once scaled with the size of the list now executed in a single step. Appending data is efficient, but removing an element from the middle of a sequence demonstrates the structural flexibility of pointers. In a linked list, deletion is a logical bypassing operation. We update the preceding node's next pointer so it points to the target node's successor. The targeted node is now orphaned, no other node points to it, and it is disconnected from the sequence. Python's garbage collector identifies this orphaned object and reclaims the memory space. Pointer rerouting makes deletion fast because it eliminates the need to physically shift subsequent elements to fill a gap. Yet, the singly linked list is limited. Because the pointers only face forward, you cannot step backward. The only way to return to a previous node is to restart traversal from the head. To enable reverse traversal, we move to a doubly linked list. This requires adding a second pointer to every node. Now, each node carries a next and a previous pointer. This establishes a bidirectional flow, though it increases the memory footprint for metadata storage. Appending data now requires wiring multiple connections. The new node links to the old tail links back, and the master tail reference updates. This sequence is fragile. Executing pointer reassignments out of order destroys the chain's references. Doubly linked lists trade memory overhead and pointer complexity for the capability of bidirectional traversal. Once you can control these links, you can move beyond linear structures. By routing the next pointer of the final node back to the head node, you create a circular linked list. This mechanism is used in round-robin scheduling algorithms in operating systems and turn-based logic in multiplayer games. Pointers can also build grid topologies. By assigning pointers for north, south, east, and west, you can represent multi-directional spatial data. Pointer architectures allow software to physically map data in ways that represent nonlinear, real-world spatial relationships. We gain structural flexibility from pointer networks, but we lose the mechanical simplicity of contiguous arrays. Every pointer used to build these connections increases the total memory overhead of the data structure. Because modern hardware is optimized for spatial locality, an array will always process purely sequential reads faster than a scattered linked list. Choosing a data structure is a negotiation. You sacrifice memory space and simplicity to gain dynamic resizing and complex structural relationships.